Alright guys, so today is the day where we finally get to start kind of the real deal, organic reactions here. We've done a lot of work getting ready to kind of take on this point in time. And essentially what we've been doing so far is kind of like building a toolbox that has lots of tools, lots of kind of just basic foundational understanding that you can then take and apply in, any kind of different circumstance. And I'll give you a heads up, I know some of you all may plan to go on and take like a full organic chemistry class in college. And if you get there, you may be like, wait, Ms. Harris didn't teach us all this stuff. So one, kind of a few considerations. One, we're about, 3 weeks short kind of on our school year due to the kind of closing period before spring break and that little week after. And two, your organic chemistry in college kind of spans the entire year, so you have like 2 semesters worth of it. And plus, this course isn't necessarily designed to be an organic chemistry course, but just to expose you kind of briefly to some of the topics that you may see down the road and just kind of get you excited, about what you can do and what you can learn at the molecular teeny tiny level. So anyways, just keep that in mind as we're going through that we're not going to cover every single facet of this because it can get a lot more complicated than what we're going to make it, and there are oftentimes many more factors like to consider. All right, here we go. So the first class of reactions that we're going to look at is called a substitution reaction. We'll also cover, kind of throughout our time together, we'll cover addition reactions and elimination reactions, kind of within our alkane section, alkane, alkene, so on and so forth. And then eventually we'll move into different functional groups and address some different reactions there. And so our learning targets today are to differentiate between nucleophiles and electrophiles, to 2, use curved arrows to show electron movement during a substitution reaction, and then 3, predict the products of a substitution reaction. And so what I'd like us to do first is kind of show you how some of the tools that you've learned already can be put into place before you really know a whole lot, about what a substitution reaction is. And so we're going to take those 2 kind of famous reaction questions. What bonds are broken or formed? And then where are the electron-rich and electron-deficient regions within the reactants? So we're going to take those questions, try to answer them, and see what insight they can give us into a substitution reaction. Now already, just by that name, substitution, you may be thinking, some things are going to swap places. So let's see kind of what happens there. So let's start with our first question. What bonds are broken and what bonds are formed? And if you want to, kind of challenge yourself a little bit, you can pause the video, try this on your own, and then watch and see how you did answering those questions. All right, so let's get started on this first example here. So here I notice from reactants to products, I have broken this bond between the chlorine and the first carbon. Then in the products, I have made a new bond between K and Cl. In the products, I've also made a brand new bond between the oxygen in this OCH3 group and carbon 1. So here's a new bond there. All right, now it wants me to label where are the electron-rich and electron-deficient regions. So electron-rich regions, remember those are lone pairs, negative charges, pi bonds. So I've got some electron-rich regions in that chlorine. It's also going to be partially negative charged because it's attached to a less electronegative carbon. And I also have kind of an electron-rich region there with the negative charge on my oxygen. As far as electron-deficient regions go, this carbon, that carbon 1, is going to be partially positive because it's attached to a more electronegative chlorine. And then I also have kind of a full positive on this potassium ion here. All right, so now let's make some observations about these next 2 examples and see if we can start developing some patterns. All right, so from reactants to products, it looks like I have broken this bond between the iodine and the CH3. And in my product side, I formed a new bond between sodium and iodine And I also have a new bond between sulfur and the CH3 group that was originally attached to the iodine. Okay. Now if we go through and figure out where our electrons are, so electron-rich regions, we definitely have the sulfur with those lone pairs and full negative charges, and also this iodine. Since it's attached to a carbon, it's going to be slightly kind of negatively charged there. All right, now let's go ahead and look at our electron deficient regions. One of those, which would be the sodium here, all right, with that nice positive charge. And then this carbon that's attached to the iodine will be slightly partially positive, okay? All right, so it seems to form kind of the same general pattern, is that you're breaking kind of a bond to carbon, and you're forming a brand new bond to carbon just with a different group substituted in. All right, in this case though, it looks like you have a sulfur kind of at play, but we are still forming a new carbon bond as well. So we're breaking a bond to carbon and we're forming a bond to carbon. All right, now let's consider this last one right quick. So what bonds are formed, what bonds are broken? So it looks like my bromine is no longer attached to carbon 2, so that bond will be broken. But I do have a new bond between hydrogen and bromine, and a new bond between carbon 2 and the hydroxide ion in water. And so now if we'll kind of label our electron regions there, this bromine is going to be slightly more electronegative, so it'll take on a partial negative charge. As a result, this carbon 2 is going to be slightly partially positive because he's less electronegative. Then if we kind of look at the water, there's kind of 2 points of view we can look at it as. So if we kind of look at it as its bent molecular structure, that oxygen is going to be partially negative, and these hydrogens are going to be partially positive. Okay. You can also kind of think of water from the perspective of an acid, where it's made up of an H plus and an OH minus ion. And from that perspective, it kind of gives you the same results. Hydrogen is electron deficient, and oxygen in that OH group is electron rich. All right, so let's take note just right quick kind of of our general observations. So we have a bond to carbon is broken. And a new bond to carbon is formed. Okay. And then what swaps places are kind of two, I guess, more negatively charged things, or two more electron-rich areas. What swaps places are two electron-rich regions. All right. So now what we're going to do is we're going to take those patterns and we're going to pull back that first example and look at that electron distribution a little more closely. And this time, try to do that last thing and draw in some curved arrows to show the way the electrons are moving. So what we marked is we said that the chlorine and kind of the oxygen and the CH3 were more of our electron-rich regions. The carbon and then the potassium are more of our electron-deficient regions. So you've got that partial positive charge there. Okay, so now if we look at the products, let's try to predict the way the electrons will flow. Now remember, the electrons always flow from the rich area to the deficient area. So to form the new KCl bond, I can have electrons flow from KCl to potassium. And to form the new oxygen to carbon 1 bond, I can have electrons flow from the oxygen to that carbon 1 bond. And that will account for the new bonds that are made. And so what this does is brings us to the need to introduce two important terms within a substitution reaction. And those terms are nucleophile and electrophile, all right? And so if you've taken, Latin or something, you may recognize that phile, or done some like Greek or whatever. But that phile is kind of has a tendency, there we go, to be associated with the love of something. For example, like Philadelphia is often termed the city of brotherly love. One of the words for love in the Bible is phileo. And so a nucleophile is a lover of nucleuses or nuclei. An electrophile is a lover of, you guessed it, electrons. And so the nuclei of something is positively charged. And so nucleophiles like to interact with things that are positively charged. And that's because they are reactants that tend to donate electrons to form a new covalent bond. Okay? And so, for example, in our picture here, the OCH3, that would be considered a nucleophile. It has a negative charge, and it's going to interact with a positive charge by donating its electrons to form a new covalent bond. On the other hand, an electrophile is a reactant that accepts a pair of electrons with the same result, forming a new covalent bond. So, this carbon right here could be called the electrophile. It's partially positively charged, so it loves electrons. It wants some negative charge to help balance it out. And so it will accept a pair of electrons from that oxygen in the process of forming a new covalent bond. So we see that nucleophiles and electrophiles work together, okay? And oftentimes this kind of pairing of a nucleophile and electrophile is what's behind sort of an acid-base reaction. Okay, so now right quick before we go on, let's introduce just a few other components of a substitution reaction. So we've already introduced this idea of the nucleophile, someone who's electron-rich, who can donate electrons to a positively charged kind of region. And we've also identified the electrophile, okay? So the nucleophile is the species that's donating electrons. The electrophile is a species that accepts electrons. Now specifically, we labeled the electrophile as this first carbon, but oftentimes when the word electrophile is used, it more frequently refers to the entire molecule that contains that positive site that the nucleophile will interact with. Okay? Now sometimes that electrophile is often deemed what's called the substrate, and that's kind of referring to it as the entire molecule upon which the reaction will take place. Then the product, of course, is the substance that will be formed from the reaction of the nucleophile and electrophile. So here's our product in this case, that with that new covalent bond between the oxygen and carbon 1. And then here's the last one that's kind of interesting and a little bit different. The leaving group, all right? And the leaving group is going to do exactly what it sounds like, and it's going to be leaving the molecule. And so the leaving group is the species that's going to break off of the original electrophile. So here, that's going to be the chlorine, because it's going to leave the original substrate or electrophile, and then kind of be paired up with another ion on the product side. Okay? And so there are these kind of four components that you'll see consistently throughout a substitution reaction: nucleophile, electrophile, product, leaving group. And so now let's kind of ask another question. How does this actual substitution, kind of the swapping of the nucleophile and the leaving group, actually take place? And that's what, when we say substitution, let me kind of pencil this in for you. That's what we're doing, is we're substituting the nucleophile for the leaving group. So that's the substitution that's taking place. Substituting the leaving group, that's sometimes abbreviated LG, by the way. Substituting the leaving group for the nucleophile. All right. So now what we're going to ask is, how does this substitution actually happen? And so we're going to introduce this kind of idea of what's called a mechanism. Okay? And so when we ask, how does something happen or how does it work, that's what a mechanism is referring to. And so to kind of introduce this, let's tell a story of a few cats and a really comfy little cat chair. And also these notes and kind of examples are from masterorganicchemistry.com. So thank you to them for putting this out there for us to use. All right. So here's the story of the two cats and a comfy chair. We have kind of two little options here. We've got option 1 and then option 2. So in the first option, you'll notice that what cat 1 is doing is he is waiting for cat 2 to leave. Then he's able to sit in the comfy chair. All right. So he waits. Cat 2 leaves, then sits in the comfy chair. All right. Now option 2 is a little bit different. In this case, cat 1 does not wait, but he kicks cat 2 directly out of the comfy chair, kind of all in one step. So there's one step. He's not waiting. Cat 1 goes in while cat 2 goes out. In the first option, it was kind of a two-step. There was the wait, and then the enter into the chair. All right. Now what we're going to see is that this cat story is actually an analogy for two possible mechanisms that can be used to accomplish a substitution reaction. You can either have wait and enter, or kind of a one-step mechanism where everything takes place in one time. Now to kind of give you some identity to these cats per se, cat 1 is going to be representing the nucleophile, all right? He's the one that's coming in. And then what cat 2 is going to be representing is the leaving group, all right? So that will kind of help you keep track of what's what as we go throughout. So the leaving group can either leave on its own, or it can be kicked out directly by the nucleophile. And so what I'm going to try to do for you briefly is kind of just draw out a small kind of representation of how the mechanism can occur. So the two mechanisms are called SN1 and then SN2. The SN1 is going to follow the option 1 cat story, and the SN2 is going to kind of follow the option 2 cat story. And we'll try to kind of point out those connections as we go along. Okay, so this is option number 1, and this is option number 2. All right, so let's start with option number 1. So to give you a sense, I'm just going to kind of make up a molecule here, and then we'll work through the steps together. So let's do an alkane with maybe bromine on the end, and I'm going to draw in the hydrogens on this first carbon. That way we can kind of keep track of how their orientation kind of changes during this reaction. Now keep in mind, a wedge, that dark triangle, means that that hydrogen is sticking out of the paper towards us, and that dash means that the hydrogen is sticking into the paper away from us. All right, so step 1 of this mechanism is you're going to have the loss of the leaving group. So what happens is these electrons here are going to be kind of given to the bromine, all right? And so at this point, what will happen is if we've lost electrons that were bonded to this original carbon, what's going to happen is that carbon will now become a cation, all right? Oops, and so we don't have this last bond anymore. But this carbon is now a cation. All right, and so I'm going to draw in a little positive charge, and that positive charge will technically be held in kind of a free p orbital there. And so let me draw in the p orbital maybe in a different color for you. Sorry, it's not a super great p orbital. Anyways, y'all know what I'm talking about. So this is a positive cation in a p orbital here. All right. So now our nucleophile, we're going to make it water, all right? So our nucleophile is going to be water. So let's draw out our little water molecule. Okay, So now this oxygen with this positive or partially negative charge can now come attack that positive cation that's just been generated. Okay, so we have kind of this cation intermediate. Okay, and specifically it's on carbon, so let's call it a carbocation. Now, kind of the neat thing is that this oxygen from the water can come in on either side. He can approach it from the left or approach it from the right, okay? And so what that can generate is potentially two different products. The products will be the same in terms of the atoms they contain, but they'll be a little bit different as far as which direction the oxygen is facing, whether from the left or from the right. Okay, so let's go ahead and proceed now. So let's pretend that the oxygen is going to approach it from the right. And so what happens is we're going to have that new bond to the oxygen, and our hydrogens are still going to be attached. Okay, so one pair of lone pairs was used in making the bond, so the oxygen now just has one set of lone pairs. And so what that does is that now gives that oxygen a full positive charge. Okay, so now the last step is we need to kind of clean up our molecule and get rid of that positive charge. So the third step that we're going to encounter is we're going to deprotonate, which means that one of those hydrogens is going to leave. So we'll have our hydrogen, it'll kind of take its electrons with it, and what we'll be left with is our molecule with just an OH group on the end. There we go. And so, whoops, I didn't mean that hydrogen. I drew the arrows the wrong way, sorry guys. The hydrogen will kind of redonate those electrons to the oxygen to give it that new lone pair. And then it'll go on its way as a positive proton. So we've lost that positive proton over here. All right, and then this is our final product. Okay, so we've substituted the bromine for the OH. And the bromine, what happens to that guy is when he leaves, he becomes Br negative. He's taken his electrons with him. And so at the end, kind of that hydrogen that's positive and that bromine that are negative can kind of pair together as an ionic compound. So you'd have like HBr. Now again, the other option is if that oxygen came in from the left side, you would get the same product, but what would happen is the oxygen would just be attached to the left instead of to the right. So let me draw that other option in. Okay, so you have kind of two different what are called stereo isomers, where you can potentially have a different kind of arrangement or different spatial arrangement of the atoms, or different stereochemistry, I guess. I know we didn't really touch on that, so I'm trying to, I guess, do the best to say it without being super confusing. Okay. All right, so there we go. Those are our products, and this would kind of be the main products for the reaction. And we'd have kind of both options, the oxygen on the left and the oxygen on the right. And let me right quick, just before we move on, kind of write in the steps again. So the first step was loss of the leaving group. The second step, we had the formation of the carbocation. And that's kind of, I guess, goes here. So loss of leaving group, and I'll put and formation of carbocation. All right. And then third step is the attack of, or second step now, I guess, is the nucleophile attacks. And the attack just means it's coming to interact with. And then finally, kind of the last step is we have deprotonation. So we lose that hydrogen. Okay. All right. So there we go. All right. So it's kind of a lot. First time you see a mechanism, it can kind of be like, whoa, this is overwhelming. But just hang in there. Again, this is just to expose you to some different things. It's okay if you don't, get everything the first time through. All right, so now for the little simpler one, which is the SN2 mechanism. This one is also sometimes kind of nicknamed the backside attack, okay? And so what will happen is we'll kind of result in the same substitution, but it's going to go about it a little differently. So we're going to actually start with kind of the similar starting substrate that we did with the bromine here. Draw in our hydrogens, okay? But we're going to use a slightly different nucleophile this time. We're going to use a nitrile group, which has a carbon triple bonded to a nitrogen with a nice full negative charge there. Okay, so now what's going to happen is kind of all in one step, the nitrile group will attack this back carbon at the same time that the bromine is leaving, okay? And so what happens is kind of in the middle, this creates sort of a transition state where you have the nitrile group kind of coming in, and then at the same time, you've got that carbon, kind of the center of where everything's happening. You have the bromine leaving. Draw the carbon a little better. There's the hydrogens. Okay. Then you have the bromine leaving. If we label our charges there. And what this creates is what's called a transition state. All right. So it's kind of an orientation that the molecules pass through where there are partial bonds. And then finally, what results at the end is you have your product, where you have the carbon and nitrogen now attached in the place of where the bromine used to be. And what happens is it always creates kind of an inversion of the stereochemistry or arrangement. Okay? And so what happens is you have kind of the carbon and nitrogen on the left side, while bromine had originally started on the right side. All right, I think I realized I shouldn't have made that a hydrogen, but it'll kind of still serve the same purpose here. Here we go. Erase that from the others. Okay, so now kind of what's left at this point is just to, practice. And so let's scroll down right quick. Oops, no, I forgot. I wanted to say one more thing. Okay, sorry. I know, guys, this lesson normally in class would maybe take, 2 college class periods, maybe 1, depending on the day, and that's like 50 minutes. So sorry, it just takes a little longer to get through this stuff, but I appreciate y'all hanging in there. Okay, so now it says, how does reaction mechanism explain the following substrate effects? So there's kind of 2 things that we want to think about here. Is that when the substitution reaction is proceeding via an SN1 mechanism, what happens is that a carbocation is formed. And so this is where one of your tools is going to be helpful, in that the more stable that carbocation is, the faster the reaction is going to proceed. So for example, when you have a substrate that is tertiary and it forms a cation, we know that a tertiary cation is more stable than a primary cation. And so that's the main consideration when you're doing an SN1 reaction, is how stable is that intermediate carbocation going to be. Now, on the other hand, for an SN2 reaction, it doesn't form a full carbocation. Instead, everything happens in one step. But because everything's happening at once, sometimes it can get a little crowded. And so what happens is the bigger and bulkier the group is, like something tertiary, it's actually going to slow the reaction way down. And so the main consideration for SN2 reactions is what's called steric hindrance, all right? And so what that means is the bigger and bulkier your electrophile, your substrate is, it's going to slow down the reaction by kind of hindering that process of everything happening at one time. All right. So now we're going to enter into kind of some practice problems here, just to help you get a sense in a small way, for some of the things that we've talked about. Okay, so I'm going to go ahead and get you started on a few of the practice problems, hopefully to make them a little easier. That way it shouldn't take you but a few minutes to kind of finish up once we let off the video. So question 1, it says, out of each pair of compounds, pick the one that will react most rapidly in an SN2 reaction. So if we think back, the SN2 reaction is the one where everything happens in one concerted step. You have the leaving group leaving at the same time that the nucleophile is coming in. And so what affects the rate of the reaction is the steric hindrance from the molecule that contains the leaving group. If it gets, in the way, which one will kind of be easiest for everything to interact on. All right, so let's take a look here. So you've got your leaving groups kind of on each of the molecules, which in this case are bromines, iodines, and chlorines, so all halogens. And so let's take a look at A right quick. And so in each of them, the carbon that is attached to the leaving group is going to be where all of this reaction is taking place. So for example, in A, this carbon will be the one that gets attacked by the nucleophile. It'll be this carbon for the next compound. For B, it'll be the carbon attached to your bromine that gets attacked kind of by the nucleophile. And so the question we're wondering is, which of those carbons is least sterically hindered? So if you notice, kind of on A, here in this first one, we have kind of a branched group coming off, while in the second example, we have more of a straight chain. Branched groups tend to be more sterically hindering. They're kind of bigger, bulkier than just a straight chain. So this chlorine is going to be the one with kind of the most steric hindrance. So the most hindrance. And so that means that this other second compound is going to be the one that reacts more rapidly. It has less stuff to get in the way of that one-step process. All right, and then B and C kind of follow that same line of thought. Here, there's more hindrance kind of by this big, bulky group. So that would make the second option, again, better because it's less sterically hindered. All right, C you can kind of figure out using the same line of thought. And then D right quick is a little different. Here the molecules have the same structure, they just have a different leaving group. So your question is, which leaving group will be better at bearing the negative charge when it leaves? And so this goes back to some of the tools that you were building in terms of which of these groups can better stabilize a negative charge. Because iodine is farther down on the periodic table, it's going to be larger, which means it is more polarizable, or it better handles that extra negative charge. So because iodine is a better leaving group, it's better able to hold that negative charge once it leaves, that molecule will react faster. Okay? Then, kind of the next part is the same. I think it should say SN1 reaction. I'll go back and change that here in a second. Okay, there we go, got that fixed. Okay, so now we're thinking about the one that will react most rapidly in an SN1 reaction. Now again, the SN1 reaction takes more than one step, and the big key factor is forming the carbocation kind of as an intermediate in the middle of the reaction. So the one in this case that's going to react most rapidly is whichever one will generate the more stable carbocation. And so again, the carbocation will be generated on whichever carbon is directly attached to the leaving group. So for example, in A, you'd have your carbocation here, you'd have your carbocation there. And so this is where you apply your knowledge of which carbocation will be more stable. Here in A, this is a tertiary carbocation because after the leaving group leaves, it'll be left with being attached to 3 carbons. Here, once the leaving group leaves, this will just be a primary carbocation because this carbon will only be attached to one other carbon group. And so as we learn, tertiary carbocations are more stable than primary carbocations. And so that will make this first group better at reacting or react more rapidly in an SN1 reaction. All right. So you should be able to go through and kind of figure those out, again, based on carbocation stability. And then the D, kind of just like before, this is a question of leaving group. The OTS, that's kind of an abbreviation for a bigger kind of molecule called a tosylate. And I left you a little note. You just need to know that that's a very good leaving group. And typically better leaving groups give you better rates of reaction. All right. So now let me help you out on just one with number 4 right quick. So number 4 says draw the carbocation intermediate that would be generated by each of the following alkyl halides in an SN1 reaction. So again, the carbocation will be generated on the carbon next to the leaving group. So you'll draw in kind of the rest of the molecule. The leaving group will be gone at this point, so you'll just be left with the carbocation at that particular carbon that was next to the original leaving group. And that same thing will apply kind of for the rest of the examples. All right, then 2 more let me help you with. So number 5A, it says for each of the following reactions, draw the mechanism for SN2. So we know that the SN2 reaction is one that occurs kind of in just one concerted step. So what we've got happening is I'm going to kind of redraw it at the bottom here just so you can see more clearly. So we've got the bromine, and this sodium with the NaSH, it's going to be an ionic compound, and so it will kind of separate into sodium plus 1 and SH, sulfur and hydrogen, with a minus charge. So that negative charge on the sulfur and hydrogen will be kind of our nucleophile. Again, the attack is going to occur at the carbon connected to the leaving group. So what we're going to do is draw our mechanism where we have the negative charge coming in to that positively charged kind of partially cation there. Not a full cation, but partially charged carbon. And then at the same time, that bromine is going to be leaving, all right? So that's the mechanism. The nucleophile attacks as the leaving group leaves. And what that results in is, as our product, we have the SH attached, and we no longer have a bond to bromine. So that kind of becomes the new molecule. And if we drew it a little more kind of formally, it almost kind of flips, the molecule's orientation. So that's kind of the same thing. This is just kind of the more correct technical structure. And then bromine, of course, would kind of be left by itself, and it would kind of pair up with the sodium ion to kind of neutralize a little bit. All right, so there's your SN2 reaction. Let's try it with an SN1 right quick. So what about number 8? It says draw the mechanism for the following SN1 reaction. So this one will proceed stepwise. So first, let's kind of redraw our molecule here. And again, all of the action is going to take place on the carbon directly connected to the leaving group. So that's this guy right here. So step 1, the leaving group will leave. So we've got the bromine kind of off by itself now. Still got our molecule. And so what will happen is we'll now have a carbocation at that carbon where the bromine left. All right. So now at this point, our nucleophile, it's the same as the last one we worked, where you have an SH with a negative charge. Our SH with a negative charge can now come in and attach to the positive carbocation, right? So in this case, what we'll result with is now an S and an H kind of attached in the place of the bromine. The bromine, that's a negative charge, will kind of pair up with the sodium that's a positive charge to form an ionic compound. Now I notice what makes this a little bit different than the SN1 example we did is that we don't have to deprotonate the sulfur at the end. In the product, the hydrogen stays attached. It's one ion, so those will stay together. All right. So I think, yeah, okay. So I think that gives you a taste of some of the different reactions. Again, guys, thank you so much. Normally this would take several, like I said, several classes, lots of practice in college, and we tried to condense it down into one day. So y'all are the best. Again, ask your questions, and we'll be glad to help you out. Thanks so much.